All right, guys, let's take a look at this thing here. Number 1.
C.
Yeah, C. Nice. Just set the thing, everything on one side, set it equal to 0. No problem. Number 2.
A.
So, in order to be a level curve of a function, how many variables can it involve? 2 in a way, because it's got that inherent z output kind of next to it, right? How do you find a level curve? What do you do to the thing to find a level curve?
Set one variable equal to one.
Set one of the variables equal, set the dependent variable equal to something, right? And that tells you what it is at various levels. So, what can this be regarded as? It looks like somebody put a 0 in place of possibly a W. So it's got to be actually A. It's not a level curve because how many variables are my inputs made up of? It's 3, so it's got to be a level surface. My inputs are 3-dimensional themselves. Holy crap. Right, and that's the one that in the book they talk about how they use color to represent the various outputs of various different inputs. And of course, the minute you get beyond 4 to 5 to 6 to 20 to 300 dimensions, you're like, well, let's forget trying to make a visual, right? So number 2 can be regarded as a level surface of the function, and we actually used that fact last time. Number 3.
B.
All right, I get a few that say C, a few that say B. Nobody's saying A, which is good. Uh-oh, unless you thought it was A, now you know it's not. It's not A, I'll tell you that. That doesn't necessarily mean it has to be B, but that's a good option. And why do you think it's C? Can a normal vector lie? Can a normal vector to a plane lie in that plane? No. So that's an automatic one to throw out. Yeah. So definitely part B. I thought more people would have said A because you see that orthogonal word and you know that the gradient has orthogonality with something. So you're like, that must be it. Because it's a gradient symbol and says the word orthogonal, that's got to be it. But no. In this case, the orthogonality of the gradient is what makes it the candidate for the normal vector, because it's orthogonal to all the vectors in that plane. That's why it's parallel to it. That's the one I want. And they say parallel because it doesn't matter how long I make the damn thing, as long as it's pointing in the right direction. What about number 4? Let me ask you this. The function they give me, how many ways is there to take the derivative of it? 2 with respect to x, with respect to y. So what can you automatically throw out? A, because they got to respect to z somehow, right? Okay. And I want to make this point. There were 2 different ways to write. There was the implicit way and the explicit way. This is where you have fx, fy, fz, because you have all those in there. The funny thing about this one is, if I just subtract the z over, I get that idea, don't I?
Yes.
So fx, fy, what would fz be? Negative 1. Yeah, so in this case, 4b. So my point, they make this huge point about the different ways to write a function, but the math shouldn't care. There should be the same stupid procedure. It is. They make this big deal. It's not really a big deal, yeah.
Why does it become negative, minus c in the input?
Because you want it to figure out what the f function is. In general, to figure out what that f function is, you set the thing equal to 0. You move everything over. So I could have went the other way, which would have just been negative f, positive 1, but that would have still been parallel.
Yeah.
Okay. Or proportional. Someone didn't want to use the word proportional. What about number 5?
C.
So why is 5 silly? It's actually the same question as, can you tell me the tangent line for that line? I'm going to call this line L. What's the tangent line for that line? at any point, L. It's already a straight line, right? So if I have, and here's what I want you to realize. We call this linear and we think it's because it's a line. No, it's linear because the variables involved are to a first power. You with me? So a plane, we still call that a linear approximation because all the variables are to a first power. So if we already have a plane, what's the tangent plane at any point going to be? That plane. So the answer is A, if I remember correctly. Yes, cool. 5A. So if they give me a plane, what's the tangent plane going to be? That plane. It's got to be just like that. That's kind of silly. Give me the line. What's the tangent line? Well, you already gave me the line. It's the line. Number 6.
Okay.
That's some deception. So the linear approximation to the surface. So how do I find that? What's another name for linear approximation to a surface? Tangent plane. I like it. How do I find what I need for that tangent plane? How do I get the normal vector? Gradient. I love it. What's the gradient of this? Oops. Be careful. No, we can do it. Personally, I like to do it this way, but we can still do it that way. What would this be? This would be fx, fy, -1. So what's fx? 2x. Fy? 2y. So what is, let me see, where am I at? Here we go. So at the point 1, 1, 2. So at the point 1, 1, 2, this normal vector becomes 2, 2, -1, right?
Yeah.
I'm missing something. Oh no, I'm fine. All right, cool. All right, cool. So then what?
They just subtracted x and y to you have a negative.
Oh yeah, they put it in a strange format just because they wanted to.
Format.
All right, that's fine. Let's see.
C. And have z minus x squared plus minus y squared.
Well, let's put this thing together. What would this look like? This would be twice x minus 1
Yep.
plus twice y minus 1 minus 1 times z
No.
minus 2, right?
There is no z variable.
No, it's
There is a z variable, definitely.
-1.
What's that?
-1.
What was this for? Wasn't this the gradient here?
Yeah.
Because if I pull this z over, doesn't this become minus z? So isn't that -1? Right? You with me? So if you make it equal to 0, which is the way that I kind of always automatically do it. I don't like this other method. I really didn't cover it too much because it's just easier just to do this. All that is what? All that represents is the gradient, which gives me my normal vector, right? So the minute I find the gradient, that gives me my normal vector. When I do the point, so there's my normal vector. What does that normal vector, what is it used for? The coefficients, right? We'll go so far. So then what do I get when they didn't simplify it all that much, did they? So let me just leave it like this. They left it like this, and all they really did was solve for z, right? Yeah, they just solve for z. So you get minus z plus 2. So if I pull the z over, z equals twice x minus 1 plus twice y minus 1 plus 2. So that is option A. Cool. So I think if you look at it, the linear approximation formula, it was back on page 846. So here's the formula. If you want to use the formula directly, you can. But I really want to make the connection between what a linear approximation is formula-wise and what it is visually. What is a linear approximation? It's the tangent plane, right? So they should be one and the same. Finding one should find the other one. The only difference with the linear approximation is you always solve for z at the end. It's supposed to be an approximation for z, for the output. When you put certain inputs into it, it works close to those inputs. Right? It works around a certain point. So if you put something in there close to that, it should give you an approximation for what the output does. So this formula is this. And of course, I'm leaving out my poor little x minus a, y minus b. And if I subtracted that over, wouldn't that, well, it's hiding a little bit. It's hiding the fact that my fz is really 1 here, right? But this is still a plane. It's going to be z equals this business here. That's what z1 is, right? That's like the c from my point here. Not there. Where's my point? There. Thank you. So that's like the c from my point. But I hate learning more formulas than I need. To get a linear approximation, it's just find the plane. And then solve for z, solve for your outputs. Yeah?
So like we are saying that the final z is the original z plus the change in of the derivative in the x direction multiplied by
Yeah,
the
exactly. It's where you start. And so it's really exactly like this. Because you start here and you go this direction. Right? That's the idea. So I start here. There's like my z1. That's why I call that z1. There's my z, there's my z1. I start there and I go this way in this direction and this much in this direction. Same idea. Yeah.
Is your Z1, is that basically just your Z point, you know, the initial?
Yeah, the
point?
2.
Yeah,
Exactly.
so, okay.
So the idea is simple. If I start at a point and I know how much it changes in certain directions, and I take a step in those directions, I know how much my output should change, roughly. So this is called a linear approximation because as I'm doing that step, my actual surface could be doing almost anything. It's just changing however it wants to. My linear approximation is a plane right there. It's going to very quickly get worse and worse and worse, possibly. Unless my surface is pretty damn straight, too. Right? So this is called, that's the idea of local linearity. The more you zoom in on a function, the more linear it looks. On this case, the more you zoom in on a surface, the more flat it looks. Okay? Earth looks very flat to us because we're standing on the freaking surface, right? If I step back to the moon, it looks like a big old ball. Same idea. Okay, so on that one was A. Yeah, 6A. What about number 7?
B.
That sounds a lot like the one we just did earlier with percent change in the volume. So I heard a vote for B. Vote for B or vote for A. Any other votes? Is that it? So let's take a look here. So obviously the function I'm working with is the volume. And they want to know the approximate change in the volume. So of course, what will that be in symbols?
F of
Partial with respect to L.
Yeah, I like it. FL
DL
DL plus HDH plus.
FW EW.
Now one thing you can tell right off the bat, and that's calling this thing F, just to make sure everybody understands. So anyway, looking up, they're saying, I don't see any freaking F. That's the F.
You can immediately cross
You
out
can immediately cross out
F of HDH.
the DH part because they tell me the H remains constant. Always nice to eliminate work at the beginning of the problem. Right? This part I don't need because DH is 0. Cool. And the rest of these kind of fall into place. What is FL? WH
Point.
plus
LH.
LH DW. Now here's the question I always get. Which value should you plug in?
Initial.
The initial value, of course. Right? Because that's the part that I'm stepping from. I want to start where I start, and then it's approximation based on rates of change from that point. So I always have to use the initial here. So initially W is 3, and H is stays in 1. And how much is L change?
Plus 0.2.
0.2, positive 0.2. That's a key way to say that. Here L starts off at 4. H is 1 all the way through. And DW is negative 0.2. Cool. Because of course it decreases. So it's just like putting a negative in for that change we did earlier. That percent change, it decreased, so we had to put a negative in.
You put in the exact values. Why did you not put in the? Why did you not calculate the percent change?
I could do it that way, but they're not asking me for percent change.
The approximate change. Okay.
Just the approximate. They want the actual change, not the percent change. So I don't have to make a ratio here. And I just got to do the work. 0.6 minus 0.8 is negative 0.2. So it looks like it's B. 7 is B. Right, G. What about number 8?
C.
Yes, C. That was pretty nice. That should have been pretty nice. Number 9?
B.
Again, all you gotta know is your derivatives, and those are easy. So that's definitely B. 9 is B. 10, I love 10.
A.
What is it? Look at A. What's kind of freaky about A? What's its normal vector? Of course, you had to calculate it, but just looking at A, what's the normal vector? It is the point, isn't it?
Oh yeah. 1, 2,
But,
negative 1.
so that point, what's another way to write that point? You could write it as a position vector, right? What should be true about a sphere relative to all the position vectors pointing to the points in that sphere? The position vector should actually be orthogonal to it. Does that make sense? Because of the symmetry of that sphere, that position vector will actually end up being orthogonal at all points. So actually, what is at the point ABC, what's the normal vector? ABC. Because that position vector is going to be the normal vector. That kicks ass. Other functions don't have that symmetry, so too bad. You got to do all the work. Spheres are beautiful. Their math should be easy. They have all the symmetry in them. Right? Not all their math is easy. Be careful. But a lot of the math should be easy. So number 10 is definitely A. Cool. All right.
Number 8 was C.
8 was C. Yes. Cool. So now, today we're going to get into 12.8.
Maximum.
Maximum, yes. And real quick, let's do a little, let me see what you guys remember about how do you do max mins in Calc 1. Okay, so if you have some function, you took a derivative,
Set to 0.
set that thing equal to 0. That gets you the what?
Critical. Zero.
Not just 0 though, what else?
Critical.
Or where
Undefined.
f prime of x is undefined. Right, this is where your critical points come from. Cool? And of course we're all hoping, please dear God, don't let the math get too much worse than this. This was pretty damn easy. This is beautiful stuff. You should go back and say, yeah, I wish everything was like that now. Find the derivative. Find out where that's 0 or undefined. And then you had an option here, didn't you? How do you actually tell if it's a max or min or some faker?
You test.
Good graphic.
Right, like, oh, I'm gonna no, not.
You calculate limits.
Yeah, same.
So you can either do, I don't know if you guys learned where you did this and you did plus, 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 minus, minus, I don't know, that's the way I used to teach it. But I pretty quickly get to the second derivative test, because you need to practice at the point anyway. And can you imagine the first option is to plot the critical points. And I used to have my students put a little Z for 0 or U for undefined.
And then you just check the signs on either side to see if it's decreasing, increasing, and then you can do like a little picture next to it. I don't know if you guys ever did that. This will give you a rough sketch. Like if it's like this, then I know let's make this 0 just for me. Yay. It's decreasing, it's 0, it's increasing, it's 0, it's decreasing. And so I kind of have a very rough sketch of what it will look like. Can you imagine what this procedure would be like now? Where you have a point that you're interested in, not just f of x, but f of x, y. And in order to make a picture like this, it's got to go on the entire plane, not just on a number line. So we quickly say, screw this. Let's do the second derivative test instead. Now, the second derivative test does become a little bit more complicated. You would hopefully understand that that's going to happen because second derivative is when partials are involved. How many ways are there to do a second derivative? Many. Right? I could do fx and fy. And then what second derivatives could I do? fx, x, fxy, fyy, fyx. And what's normally true about fxy and fyn?
They're equal to each
They're
other.
normally equal unless you have some discontinuous function. Cool. Okay, how are we doing so far? So I wanted to do a little review because a lot of these same ideas are going to pop up again. So if you understand this stuff, it should be relatively easier to understand the new stuff. So now we have some function of x and y. So step 1 is relatively the same. Except what's the one difference do you think now, of course? Partial, yeah. So I do all partials I can. So in this case, it's fx and fy. So find these. Step 2, how do I find the critical points? This is also where you got to be a little careful with your semantics.
Each one equal to 0.
Each one, exactly. I don't know if you meant to say it like that, but fx equal to 0 and fy equal to 0. I like it. So the points you find must be composed of combinations of where fx is 0 and fy is 0. They can't just be separate. They actually have to be together. That has to be that point. So if you do this and you get x equals 2, and you do this and you get y equals 1, then at 2, 1, that's a critical point. That's what that means. Okay, cool. What if you get plus or minus 2 and plus or minus 1? How many points is that? 4. 2, 1, negative 2, 1, negative 2, negative 1, 2, negative 1. I think it's the one I looked at. Okay, so we sort of start to get the feel of the ideas are exactly the same, but now of course you have all these other directions to go in, and officially one other direction really. So I've got to kind of expand my steps. It's got to include those other directions I can go in. And here's where things get really weird. Well, not really weird, but change a little bit. Second derivative, that's where we're going to spend most of our time because these first 2 steps are relatively easy. Partial should be like awesome. Give me some partial problems, please. So let's talk a little bit about why the second derivative test might become stranger. And then we'll actually take a look at what it is. I think, I could get in trouble if I try to draw this thing. Look on page, perfect, 855. If you don't have that book with you, what the hell? But also, can you remember the function we looked at before that officially looked like a saddle? It kind of leads to, I don't know if you guys remember this, but it looks like a saddle. It goes up like this and down on the sides. Yes. And we did talk a little bit at that point. I got a little ahead of myself because I wanted to get us a preview of this coming now. The very middle point is a weird-ass point. And actually, let me put it up here because I want to talk about it.